Hello everyone. In this session, we'll be looking at atmospheric pressure and pressure variation with depth in a fluid medium. Let us go. So, pressure where it can be observed. First of all, we'll see number of circumstances. So here, a beautiful picture of fountains, right? So this pressure on fluid makes the fountains, and then if the pressure is varied, obviously you will be getting smaller fountain, bigger fountain, etc. And not only depends upon the pressure, it depends upon the nozzle size also. So this you might have seen on YouTube. So here there is a play of pressure, we can say play of fluid pressure, right? Okay, here one simple example of atmospheric pressure. In the first case, the bottle is empty, right? Empty in the sense it's not filled with water, it is filled with air. And then the pressure outside the bottle, which is atmospheric pressure, and then pressure inside also is atmospheric pressure. And then by some means, if we remove some of the air from inside, what happens is external pressure because of the atmosphere will be able to squeeze the bottle like this. So more of the air from the bottle is removed by some means. So what happens is it is getting squeezed more and more. So here you can observe that the atmospheric pressure is acting always. Okay, here there is a case where pressure is used. Pressurized liquid and air mix is used for shining your cars, right? That is a usual case wherein washing of the vehicles is being done. One more case, wherever there is a tire, inside the tire also there will be air which is under pressure. We'll be seeing in later slides. Okay, pressure of air is released from the balloon. So if you have a balloon and then if you have filled up some pressurized air in that, and then if you just release it, what happens? You can see that it just flies off with making hissing sound. So that is again, there is a pressure of, presence of pressure that can be seen. Another very common example where we come across pressure is blood pressure. And you know that there are two values, 120 and 80. 120 is called upper number or systolic pressure, and then 80 is called a lower number or diastolic pressure. What is to be observed, or I want your notice to be brought to 120 and 80. We know these numbers if you have any contact with BP patients or doctors, right? But 120 and 80 represents not only just numbers, you have to tell specifically it is so many of mercury. That's the way how the pressure is said. I repeat, the magnitude of the pressure is said as 120 millimeters of mercury. What is the meaning of this? We'll see it in later stage. Anyway, the pressure can be measured in terms of millimeters of mercury. That is what we can understand. So other values, you know that higher pressures are danger, and then you have to take care and all. Okay, then here very nicely represented by a column of air above the Earth's periphery, or on the crust. If you are present, there is a good column of air which is present beyond the surface, and this height for which the air is present, it is shown like this. It is something like 10 kilometers 10 kilometers of air column is always present over our head. And then if we have 1 square inch of our thumb, 1 inch by 1 inch, the air column will be applying a force of 14.7 pounds of pressure on 1 square inch. So this itself is written as a PSI. If you can remember, the units of pressure are PSI. So how it is read is pounds per square inch. That is what it is said here, 14.7 pounds per square inch. Do you have any idea where this particular unit is again used in day-to-day life? You might have come across, but you have not observed. We'll see it in here. Whenever we fill in air, obviously we say, if you remember in your vehicles, you will fill something like 25 in front wheels, and then 33 or 35, something like that, in rear wheels. So what is this 33 or 25? It is nothing but PSI, that is pounds per square inch. Because instead of 33, if he fills 32, hardly there is any difference, right? There is no much of difference. But the same pressure, if it is measured in kg per centimeter square units, right, there will be a vast difference between 1 kg per centimeter square and 2 kg per centimeter square. We'll see it in later stages. But anyway, what one should know is pressure is generally measured whenever you fill the air. The units of measurement is PSI, and the magnitude is something like 25 to 35 as far as private owned vehicles are concerned. Right, if you go for bigger vehicles like lorries and then some other vehicles, obviously the pressure inside will be much more. That is what one can observe. Okay, here pressure variation at a point inside a fluid medium. Let us see. Here there is a column of fluid. I have shown it over here. So this is the top surface of the liquid, let us say, and then we'll consider one small cube there, right? So that is an element of study, let us say, right? Again, I'll enlarge that, right? I'll enlarge that, and O is the point of reference. X and Y are the axis on horizontal plane, Z is the vertical one. Okay, here I have represented is in this direction, that is in positive Z direction. On the bottom surface there is a pressure P, multiplied by delta X into delta Y gives the force. Delta X into delta Y gives the bottom area, and then whenever you multiply it with this is the area, bottom area. This area multiplied by P gives you the force. So that is what is the force. Now if I'll take out this anyway. Okay, here bottom pressure is this. Left side, if you look at this, the pressure is same P, because at small point we are considering, because of that pressure is P, but the force acting on this face, that is OABC, if you look at, right, the side over here is delta X, the side over there is delta Z. Because of that, the area is delta X into delta Z multiplied by P gives you a force there, right? These are the two axes on which I'm going to consider the forces. More interesting thing is this: if this pressure is P, there at a distance of delta Z, what would be the pressure? Or in this direction, in X direction, if P is the pressure on the face OABC, then what would be the pressure on EFG H, right? E, F, G, F, I think. Okay. Now, what is the pressure on this face? Will it be same as P, or there will be a variation? Here, I have considered, or I have assumed that pressure is going to change, right? At what rate it changes? It changes spatially, means when it is moved from this point to this point through a distance of delta y, there is a rate of change of pressure and multiplied by at what distance it has changed. That's how it is. To understand this term in a better manner, I got an example over here. There is a similarity. Now look at this. Here I'll start. We should know this. That is point A and point B. Velocity at A is 2 meter per second. Velocity at point B we don't know. The time at point A is 3 seconds. Time at point B is 5 seconds. Means 2 seconds I am going to move from A to B. Now to find the velocity at this point, I should know what is the rate at which the velocity is changing. Try to understand the concept here. I know the velocity at this point. I'm going from this point to this point in 2 seconds. If I want to find the velocity at this point, I should know the rate at which the velocity changes, and that is known as dv by dt, rate of change of velocity with respect to time. Let us say the value of that is 1.5 meter per second, velocity per unit time. So rate of change of velocity with respect to time, we call it as acceleration. Anyway, with this rate of change of velocity, what would be the velocity at point B? How will you calculate? Velocity at point B is velocity at point A plus the time multiplied by rate of change of velocity. So overall it gives you 5 meter per second at the end of 5 seconds. You have started with velocity of 2. The rate of change is 1.5 for 2 seconds. It will be 1.5 plus 1.53. So the final velocity at point B is this. I want to bring your notice to this. If I want some value at some other point, I should know rate of change. Now exactly to similar to this situation, if we have a point 1 with a pressure P1 and pressure at point 2 is P2 and distance from this to this is say D12. Now if I want to find P2, I should know what is the rate of change of pressure in this direction, right, with respect to the distance. Let us say here we have taken with respect to time. Here let us take the rate of change with respect to distance. Now rate of change of pressure with respect to distance, that is dP by dx. Then the pressure P2 will be given by pressure P1 plus rate of change of pressure with respect to distance, and what is the distance for which it has moved, d12. So this is the concept with which we can write original pressure P plus rate of change of pressure multiplied by the distance for which the pressure has been changed or analyzed. So I hope you have understood this particular part. So considering the same, again coming back to this point, pressure on this point or on this face is P, pressure on this point which is at a distance of delta y. If you observe here, we have moved a distance of delta y along the axis. So here the final pressure will be P, the original pressure, plus a rate of change of pressure dou P by dou y multiplied by the distance for which it has changed, delta y. This term is exactly same as this. Now this pressure intensity multiplied by the area, that is delta x into delta z, gives you total force which is acting on this face. And again, you know that in earlier discussing, we have seen that the pressure acts always perpendicular to the surface. So pressure will be perfectly horizontal because this face is perfectly vertical. Now same way, here the vertically upward pressure is P. Now this pressure will be P plus rate of change of pressure with respect to distance, right? Dou P by dou Z, dou P by dou Z, that is the direction in which the pressure is changing. Now what is the distance? It has moved from this point to this point. It is delta Z. So rate of change of pressure multiplied by the duration of distance for which it has changed. So this is the final pressure intensity on this face multiplied by delta x, and delta x and delta y gives you the force. Okay, now let's go to the next slide. So here I have kept the same figure over here. So here A, B, C, D, E, F, G, O is a small element of fluid in stationary state of size delta x, delta y, delta z. Therefore, by static equilibrium, sigma fx should be equal to 0 and sigma fy should be 0, sigma fz equal to 0. Now F ABCO, that is ABCO, is nothing but P into delta x, delta z. F DZEF DGEF, right? So this is again this pressure, this force. Here the changed pressure on the face GDEF after a distance of delta y is used. Now one more piece of information that you should know is weight per unit volume is gamma, right? So weight will be calculated as gamma multiplied by volume, and in this case the volume is delta x, delta y, delta z. Because of that, weight of the liquid or fluid involved in this particular cuboid is gamma multiplied by delta x, delta y, delta z. Now this information is useful when you write equation in vertical direction. Let us go one by one. Now horizontally, sigma fx equal to 0 is equal to first force P into delta x, delta z minus this one P plus dou P by dou y into delta y into delta x, delta y equal to 0. There is no other horizontal force. The weight is acting in vertical direction, so it's only this much. Now if you simplify this, you get that you can just see here P into delta x, delta z is there, P into delta x, delta y is there, right? So therefore what happens? Something has gone wrong. Yeah, here it should have been delta x, delta z. Y has come twice, so this is delta z. So P into delta x, delta z cancels with P into delta x, delta z with this minus sign. So you'll be left with only P into dou P by dou y into delta y, delta x, delta z. So dou P by dou y into delta x, delta y, delta z equal to 0. Of course it will be with minus sign, but if you transfer it on the other side, though there is a negative sign, it will be fine, that it will be positive. Now here as delta x, delta y, delta z, the volume is not equal to 0, it is must. So this argument is very important. You can look at that. There are two products, there are two terms multiplied and then giving you the value 0. So dou P by dou y multiplied by delta x, delta y, delta z is equal to 0. Either this has to be 0 or this has to be 0. This is not 0 because we have considered a real case element with some finite distances delta x, delta y, delta z. Though they are small, but there are some magnitude, it cannot be equal to 0. So only way we can conclude is dou p by dou y equal to 0. Similarly, I have considered this in x direction. If you go in y direction, right, then this is in y direction. If you go in x direction, again horizontal plane only, we can conclude that it is dou p by dou x is also equal to 0. Therefore, what is the conclusion? The conclusion is no change in pressure as we move along horizontal plane, whether you move in x plane or y plane, whatever. But as long as you are moving in horizontal plane, there is no change in pressure. That is what we can conclude. It's an important conclusion one should know, that in a fluid medium, if we move horizontally, there is no change in pressure, as we move along horizontal plane. But sigma fz is equal to 0. Let us say here the equation becomes p delta x delta y minus this term p plus dou p by dou z into dou z multiplied by delta x delta y minus, again there is a weight w equal to 0. Now let me substitute for this term, because this term p delta x delta y cancels with this p delta x delta y, negative. So here the leftover term is minus dou p by dou x, dou p by dou z multiplied by delta x y z. Then there is minus sign here, this minus is left over here. Now this w is coming from here, gamma multiplied by delta x delta y delta z equal to 0. I can take this common and bring it on the left hand side, so I'll be left with just this term minus this term, this is also minus, equal to 0. If I rearrange, dou p by dou z becomes minus gamma. So that is another conclusion that we can make, because this is variation of pressure with respect to z direction, that is dou p by dou z. So conclusion is the pressure decreases, because there is a minus sign, pressure decreases at a rate of gamma, as we move up in vertical direction. Means our positive direction is this way, so as we move up in the liquid, the pressure decreases by an amount gamma. Vice versa, also it increases as we move down vertically in fluid medium of specific weight gamma. If you have a fluid medium having specific weight gamma, if we move up, it changes per unit length, that is dou p by dou z rate of change of pressure with respect to distance, or you can say change of pressure per unit distance or per unit height. It will be at a rate of gamma. As we move up, it is minus, it decreases. As we move down, it increases, right? What I would like to mention here is those conclusions, two conclusions that we have made. We'll refresh them. The first conclusion is no change in pressure as we move along horizontal plane inside fluid medium. That is understandable, that if you are in a fluid medium, that is inside a fluid, and if you move horizontally, there is no change in pressure. There will be pressure, but the magnitude of pressure will not change. But if you move vertically, that is a second conclusion, pressure decreases at a rate of gamma, as we move up in vertical direction, and also it decreases as we move down vertically in fluid medium of specific weight gamma. Gamma is the specific weight or unit weight of the fluid. So with this background, we'll go further. So pressure at any point in a fluid medium. So here there is a fluid medium. You can just see there is a container, and fluid is kept inside that. That is the open to sky surface, free surface on which atmospheric pressure is acting, and magnitude of the pressure is taken as P atmospheric, and at a depth below the fluid medium at a point A, any arbitrary point A at which the depth is h below the free surface, Okay, this particular point with respect to some reference, general datum of reference, let us put it as Z. The bottom of the liquid will take it as Z naught, the total depth of the liquid as capital H. Now, from earlier discussion, we know that it is we know that dou P by dou Z, that is variation of pressure with respect to Z direction, is minus gamma. Means as you go up vertically, there will be fall of pressure at a rate of gamma. That is what it means. Now if you rearrange the terms, dou P is equal to minus gamma into d dou Z. So integrating, what we get is the P in Z direction is equal to, that is Pz is equal to minus gamma as it is, assuming that gamma is not changing, that is unit weight is not changing, minus gamma. So dou Z integrated to Z plus a constant of integration. So this we'll call it as equation number 1. Now what are the boundary conditions? We know at Z equal to, now you can look here, at Z equal to Z naught plus H, means at this surface, right, the pressure is atmospheric pressure. You can just see here, there on the top of the free surface, there will be atmospheric pressure which will be acting. So boundary condition that we know is at Z equal to H plus Z naught, the pressure Pz is equal to P atmospheric pressure. Using equation 1, we can write P atmospheric is equal to minus gamma into H plus Z naught. You can just see here information, and here this is used. So Pz is equal to P atmospheric pressure is equal to minus gamma is written. Instead of this Z, I am substituting H plus Z naught plus C is kept as it is. Now from this we can work out what C is. The constant of integration C is equal to, it becomes P atmospheric plus gamma multiplied by H plus Z naught. This is equation number 2. Now this C I'll substitute back into this so that I'll get general expression for Pz. Substituting back in 1 means the value of C is substituted in this equation. This equation is Pz equal to minus gamma Z, same equation it is, minus gamma Z plus C. The C is coming from this end. So C is equal to P atmospheric plus gamma H plus Z naught. Now if you do a bit of mathematics, right, and then calculate, Pz becomes P atmospheric plus gamma H. Here we'll be using H plus Z naught equal to H plus Z, because you know that H plus Z naught is equal to H plus Z. So that's why this becomes Pz becomes sum of P atmospheric plus gamma into H. So this is a very important formula, you can say, or equation you can say, or expression you can say, that one should remember. So first most important equation that you have learned in fluid mechanics, I would say, would be P at any point in z direction. If you want to calculate, it will be P atmospheric plus gamma h. P is equal to P atmospheric plus gamma into h. So pressure at any point in a fluid medium is a little more than atmospheric pressure P atmospheric. That additional quantity is gamma into h. So pressure at any point is equal to atmospheric pressure plus gamma into h. That is what is the conclusion one should know. Okay, what is the conclusion? Pressure at any point in static mass of fluid, mass of liquid, depends only on vertical depth. Yes, very important. It depends upon vertical depth, because in here, in earlier slide, we have seen that it is depending upon h. What is the size of the container this way or that way? It's not a matter at all. It can be few centimeters this way or few kilometers this way, right? That is not at all a point. But this particular point is at what depth from the free surface. That h matters a lot, right? So one should know that pressure at any point in static mass of fluid depends only on vertical depth of the point below the free surface, and also the specific weight gamma of the liquid. It does not depend upon size and shape of the container. So the vertical height of the free surface above any point in liquid medium at rest is known as pressure head. Means whatever we have represented as h earlier, that will be referred to as pressure head. For gauge pressure, atmospheric pressure is taken is equal to 0. We'll see in detail afterwards this one, right? Let us assume to begin with P is equal to gamma h, atmospheric pressure, you consider it as 0 for a moment. Now this h becomes P by gamma, and this is known as pressure head or just head. Now in this figure, a very famous figure where liquid is there in interesting container, and first one is having a tube like thing, second one is having a glass like thing, C is something different, D is a meandering kind of. But when you pour the liquid stands at the same level in all the containers or openings. And if you have A, B, C, D, 4 points at the same horizontal level, pressure at A, how do you calculate? Pressure at A is equal to gamma into h. Gamma is the unit weight of the liquid. H is vertical height difference from this level to this level. Now if you consider any of these points and then free surface, it is equal to h. So that's why PA is equal to PB is equal to C equal to PD equal to gamma into h. You should appreciate that it is not depending upon the size of the opening, right? Very small tube or very big tube or not shapely tube or like this, any kind of thing, right? So still it will be having value of gamma h. Here even if you put something like this, a tube which is having some shape something like that, then also the liquid will rise here at the same level. It is at the same level. So then also if I want to find the pressure at this point, right, what I should know is from this to this free surface, what is the vertical height? Again it is h, right? Whether you put a pipe like that or put a pipe in an inclined manner like that, so whatever may be, the liquid will be rising there, and vertical height difference will be h only. Because of that, PA is equal to PB is equal to PC equal to PD equal to gamma into h. So it is independent of shape and size of the container. That is what you can conclude. Okay, here I have information like atmospheric pressure. Now, how this atmospheric pressure acts, we'll see. Here there is a experimental setup that is shown. In that setup, what is done is there is a container filled up with mercury, and there is a tube which is filled with mercury, and it is made upside down, and putting the mouth of that tube inside this mercury, it is made upside down. What happens is mercury goes down a little inside, but it stops, right? Because here there is an atmospheric pressure which is trying to push this mercury into the tube, and this pressure pushes it through a height of 760 mm. So atmospheric pressure will be able to push the mercury through a distance of 760 mm. You know that mercury has got a specific gravity of 13.6. It is 13.6 times heavier than water, and such mercury is pushed almost for 3/4 of a meter, 0.76 meters. And if you put water, obviously it will be too big a height it can stand. So here I have written some things. Atmospheric pressure, standard atmospheric pressure at mean say level at 15 degrees centigrade is often used. That is atmospheric pressure. The value of standard atmospheric pressure is taken as 1 atmosphere. What is the meaning of 1 atmosphere? 1 atmosphere pressure is equal to 10.336 meters of water, or it is equal to 760 millimeters of mercury. Now, to calculate what exactly the atmospheric pressure, we know this formula now. P is equal to gamma into H, equal to gamma, if you consider water 9.81 kilonewton per meter cube, H is 10.336 meters, or the same thing can be calculated in terms of mercury also, right? So gamma has to be mercury. Gamma of mercury is 13.6 into 9.81, then multiplied by 0.76. So this also gives you 101.4. This is also roughly the same value. So atmospheric pressure value, you can assume now onwards, it can be taken as 101.4 kilopascals. Kilo stands for 10 raised to 3, pascal stands for Newton per meter square. So 1 atmospheric pressure is equal to 101.4 kilopascals. You can remember this because many times you have to use it in some of the calculations. So with this, we'll stop here. We'll meet again shortly.